Hey guys, this is Ruthvik, and in this session, I'm gonna take the PCT for Codeforces Round 1075 due 2. Okay, let's start. Coming to the first question, Peter drew a table of size h into L and initially filled it with zeros. Uh, Here the rows are from 1 to h and the columns are from 1 to L. Next, Net came up with an array of numbers a1 to an and wanted to modify the table. Net can choose 2k numbers from this array and split them into k pairs, and the value of 2k must be less than or equal to n. After that, for each resulting pair x comma y, he takes the cell located in row x and column y and adds 1 to the number in that cell. If such cell does not exist, then the pair does nothing to the table. Now what we want to do is we want to maximize the sum of the numbers in the table. Coming to the constraints, the value of n is less than or equal to 100 and the value of h and l are less than or equal to 1000. Also the elements in the array are less than or equal to 1000. I'll go through a few of the test cases. Coming to the first test case, the value of n is 2, h is 1 and l is 1. So there are two elements in the array. So what net can do is net can take the pair 1 comma 1 and add 1 to the number located in row 1 and column 1. Finally, he will be resulting with a sum 1. In the second test case, the value of n is 5, h is 2 and l is 2. So what net will do in this is uh, he can take the pairs 1 comma 2 and 2 comma 2. And he will add 1 to them and the sum will be equal to 2. And it can be shown that it's not possible to achieve a higher sum. So here basically we are given an array of size n and two integers h comma l. So in one operation what we can do is we can take any two elements x comma y from the array and uh, this pair should be valid. That is, the value of x should be less than or equal to h and the value of y should be less than or equal to l. If the pair is valid, then what will happen is we'll add plus one to that element in that location. Or, uh, or we can interpret as follows. Uh, it doesn't matter where we add plus one in the table to the total. What happens to total is if I have a valid pair, then my total increases by one. So basically, I have to maximize the number of valid pairs. Okay, so let's start with this. Let's generalize that h is less than L. In the case where h is greater than or equal to L, we can simply swap h comma L. Okay. After generalizing this, what I'll do is I will split the elements in the initial array into two categories. Category 1 contains the elements in the array x such that x is less than or equal to h, and category 2 contains the elements where x lies between h to l. Here, like the reason I am splitting into two categories is that here if I have two like a coordinate x comma y, here the x value must be less than or equal to h and the y value must be less than or equal to l, right? So while filling the y values, y can take the values both from category 1 and category 2 because in category 1 x is less than or equal to x is less than or equal to h, which is less than or equal to L. So category 1 is satisfied and also category 2 is satisfied as x is less than or equal to L. But x can only take the values from category 1. So what we can do here is simply go into casework. We'll keep the count of number of elements in each category. Let the count in category 1 be C1 and category 2 be C2. In the case where C1 is less than or equal to C2, what I can do is I will put all the C1 elements in the X, and for every C1 element, I can find a element in the array from the category C2. As C2 is greater than or equal to C1, for every element in C1, I can find a C2. So basically, when C1 is less than or equal to C2, my uh, answer will be equal to C1. Now coming to the case where C1 is greater than C2, here in the case where C1 is greater than or equal to like C1 is greater than C2, what I can do is X can take the values only from C1 and Y can take the values from C1 and C2, right? So what will happen is that like initially all the C1 values will go to X and few of the C1 values will go to Y and remaining will be filled by C2. All the C1 values will, like first few or first set of C1 values will go to X and the remaining C1 values and all the C2 values will be in Y. So here we can see that the answer will be C1 plus C2 by 2 in the case where C1 is greater than C2. And that's all. Coming to the code, we can see if x is less than or equal to h, I'm incrementing the C1 count. And if x is less than or equal to L, like it is greater than h and less than or equal to L, then I'm incrementing the C2 count. If if C2 is greater than C1, if C2 is greater than C1, then the answer will be C1. Else, my answer will be C1 plus C2 by 2. Yeah, that's all. Now coming to the second question. On an infinite number line, at point 0 sits a frog. After many years of meditation, the frog has mastered. Okay, the frog can basically make n unique types of magical jumps. In ith type of jump, it can jump forward by at most AI units. Like for example, if the frog is at point k, it can jump from any integer point to any integer point from k to k plus ai. Uh, but uh, the magic always comes with a price. It has been cursed. Before each BIth attempt, like BI, 2BI, 3BI, so on, uh, if it uses ith magic, it can jump AI units forward, at most AI units forward, right? If it uses ith magic BI times, at every BI attempt, it goes back or rolls back by CI units. Like for example, at every BIth at every BIth attempt of ith magic, the frog can land from any integer point from k minus ci to k minus ci plus ai. Like basically, initially it falls back to k minus ci, and from here it makes a jump of size ai. The frog's goal is to reach the number x using the jumps while minimizing the number of rollbacks. Or we have to determine if it is not possible for the frog to reach the point x. So the input are we are given n, the constraints on input are the n is less than or equal to 1e5 and x is less than or equal to 1e18. And we have three integers a, b, and c which are less than or equal to 1e6. Okay, coming to the explanation. Here we are given n and x and also NAI, BI, CI values. Like denotes the length of jump, BI denotes the curse attempt, and CI denotes the rollback length. Okay, at every BI step. So what we can initially do is we can see that for every I, for first BI minus 1 jumps, there are no rollbacks. So greedily, what I'll do is let the current location be 0 initially. The current location is 0 initially. So greedily, what I'll do is I'll do bi minus 1 jumps for every AI. Bi minus jumps for every AI. Okay. So how much I'll move for each I? Current plus equal to number of jumps into AI. So next, what will happen is after making these many jumps, I'll initially check if the value of current is greater than or equal to x. If it is greater than or equal to x, then with zero rollbacks, I have happily passed the coordinate x. If the value of current is less than x, if the value of current is less than x, then my situation is like this. Like for every I am at a location where my next jump is cursed. My next jump is cursed and my bi minus 1 following my next jumps are not cursed. So basically, I am currently here. This is a cursed jump, and these bi minus 1 are not cursed jump. So for every I with one rollback, the rollback will obviously happen at the initial cursed jump. So what will happen is minus ci before because of rollback, and here and after rollback, I'll move forward by AI units plus bi minus 1 into AI. Like after making a curse jump, I am free to make, I can, uh, Like it's best if I make bi minus 1 non-curse jumps, right? As there is no rollback penalty. So I'll simply add bi minus 1 into ai jumps. So basically this sums up to bi into ai minus ci. So for every I, for at the cost of one rollback, I can move this much steps forward. At the cost of one rollback, I can move this many steps forward. So what I'll do next is I'll store I'll store these values in an array. For every I, I'll store the value like let's suppose in a vector v, I'll store the values vi equal to bi into ai minus ci. So my next step will be what I'll do is so after storing these values, what I'll do is I'll sort the vector v because in the future jumps, I will choose the value I which moves the highest distance forward at the cost of one rollback. Okay. So basically after sorting the vector v, or there is no need to sort actually, I can simply take the maximum value of vector v. And let's suppose I have initially the value of current is uh, initially the value of current is after every bi minus 1 jumps I have calculated the value of current, right? With the remaining length I have to cover the x minus current. So for the remaining length, the number of jumps required are remaining length by let the maximum value of this vector be mx, remaining length by max value of the vector, and I'll take the seal of this value, and that will be my answer. Here we have to note that if the maximum value is less than or equal to 0, when this will occur is if there are very big rollbacks. Like for example, if I have a AI value equal to 2 and rollback CI equal to 10 and BI equal to some 3 or something. So for every 3 steps, like I am rolling back at first step only, right? So what will happen is if I am at a step, certain point here, I'll initially roll back 10 steps and I'll jump 3 steps forward. So here I can see is uh, irrespective of what I do, I'll end up at a location that is behind my current location. So if the value of max is less than or equal to 0, then our answer will be like it's impossible to reach x, so I'll print minus 1. So if the value of max is greater than 0, then our answer will be remaining by max, seal of remaining by max. That's all. Now coming to the code of the question. Here initially I'm taking the input and calculating the value of current. Current bi minus current is the summation of bi minus 1 into ai. And if the value of current is greater than or equal to x, then with zero rollbacks, I'm reaching the value x. So I'll return. Else, else I have made a vector v and I am storing the values ai into bi minus ci in the vector. And I have basically reverse sorted the array. This is not necessary, or as we can simply take the maximum value in the vector. After reverse sorting, we can see that maximum value lies at the position, at the first position. So if the maximum value is less than or equal to 0, then it is impossible to reach x. So I'm printing -1. Any is simply cout -1 end L. And if it is greater than 0, then I'll initially calculate the remaining distance and I'll output the ceil of remaining distance by v of 0. That's all. Now coming to the third question. We are given a natural number n and a permutation p of length n such that for each I is from here we have to note that I is from 2 to n minus 1, like excluding the first and last index. There exists a j, once again, yeah, I from 2 to n minus 1. There exists a j from I to n such that pi equal to pj's or I. It can be proved that under the constraints of the problem, there exists at least one suitable permutation P. So here the value of uh, n is bounded by 2e5, 2 into 10 power 5. For every test case, we are given an integer n and we have to output the permutation. Like for example, in I'll go through one of the test case. In the second test case, we can see that P of 2 equal to 6. Uh, that is basically what we want is P of I must be equal to P of j XOR I. Here, the I value equal to 2 and j must be greater than or equal to I. So for P of 2, we are taking P of 6 as 6 is greater than or equal to 2. P of 2 equal to P of 6 dot 2. Likewise, we can see that for all elements, the condition is satisfied. Like for all elements, we can find a j which is greater than or equal to I and P of j XOR I equal to P of I. Okay, now coming to the code, we have the condition P of I must be equal to P of j XOR I for every j greater than or equal to I. Sorry, for every I between 1 to n and j must be greater than or equal to I. Like here we are excluding the first and last index. So I'm using the symbol strictly less than. So as we are including the first and last index, let's see if I can construct a answer if I fix the last element of the permutation to be 1. So coming to the, or let's take any general element x. If if the if I fix the last element 1 and also I'll assume that always the value of j will be equal to n, as the value of j equal to n will be greater than or equal to all i's from 1 to n. Okay. So if the value of j is n, what will happen is p of I equal to p of j. The value of j is n, XOR I. P of j XOR I. So what will happen here is if the in number I is odd, if the number I is odd, then in binary representation of I, the last bit will be 1. And if I XOR the odd number with 1, what will happen is the number will become I minus 1. If if I is even, then in the binary representation, the last bit will be 0. And if I XOR the number, XOR a even number with 1, what will happen is it will result, it will increment by 1. Basically, the last bit will be 0. And after getting XORed with 1, 0 XOR 1 is 1. the last bit will become 1 and the remaining bits will be unchanged. So it will become from I to I plus 1. So here we can see that if I is if I is even, or we can generalize for any number f x. If x is even, x or 1 equal to x plus 1. If x is odd, x or 1 equal to x minus 1. So for every I, if I is even, what I'll do is I will place the value I plus 1 at index I, because if I is even, I plus 1 will be odd. And if I XOR this with 1, I plus 1 XOR 1 will be equal to I. If the value of I is odd, what I'll do is I will keep the value I minus 1 here. Oh, sorry. I won't keep the I minus 1. If the value of I is odd, we can see that I minus 1 is even. As I minus 1 is even, if I put I minus 1 at the location I and I XOR with 1, what will happen is I minus 1 XOR 1 equal to I. So basically, if I is even, I'll put P of I equal to I plus 1. If I is odd, I'll put P of I equal to I minus 1. And what I'll get is P of I XOR I will be equal to I. Sorry, P of I XOR 1 will be equal to I. Here, 1 is nothing but P of n, the last element of the permutation. P of I XOR P of n equal to 1, equal to I. So basically, what is our initial condition? P of I must be equal to P of j XOR I. With this can be rewritten as P of I XOR P of j equal to I. We can simply XOR with the P of j on both the sides, and we can convert into this format. And here we can see that that condition is satisfied, where the value of j will be equal to n. And that's all. Coming to the code, initially I am assigning 1 to the last element of the permutation, and for every even I, like starting from index 2 to index 2, starting from index 2, I'll increment by 2. So I'll only walk on all the even indices, and I'll put the value I plus 1 at all even indices. And for odd indices, the odd indices will start from 3, and I'll increment by 2. When I walk on all the odd indices, I'll put the value I minus 1. So here, for the last remaining, for the first element, what I'll put is I'll put the element that has been left out. What I'm doing here is simply I'll take the sum of all the elements which I have currently put in the array, and the element left out will be equal to sum of all, like sum of all values from 1 to n minus the current sum in the array. So after putting the first element, I'll simply print all the elements from 1 to index n. And that's all. Coming to the fourth question, here the difference in third and fourth question, like the difference in C1 and C2 is that in C1 we are given I, I is like I is greater than or equal to 2, and in C2 we are given I is greater than or equal to 1. So In C2, we have to also ensure that the condition is satisfied at the first index. And remaining part of the question is same. And in C1, we saw that the answer is always possible, but in C2, there are cases where the answer is not possible. So we have to output -1 in such cases. So here, let's first analyze the cases when the answer is -1. The answer, let's look at the case where n is a perfect power of 2, like where n is a power of 2. What will happen in that case is, I'm writing in binary representation, only the MSB will be 1 in the number n. From if we consider the numbers from 1 to n, the MSB will be 1 like at the like for example, let the number be 2 power x. 2 power x will have its xth bit as 1. Consider we are indexing by 0, 0, 1, 2, 3, so on till x. 2 power x will have its x bit as 1. And from 1 to n, the only number having the xth bit as 1 will be n. All other numbers will have this bit as 0. So basically, if I XOR n with which is uh, any other number, any other number x, which is less than n, then the result will be greater than n because n will be in this form and x will have this bit 0 and x will have any one of these bits set. Let that bit be here. And if I XOR these two numbers, what will happen is I'll have this set, this xth bit set, and also one bit, one of the lower bits as 1. And obviously this number will be greater than n. So in this case, we can see that like wherever I include the number n, like for example, if I keep it at last, I will be forced to use this number n for last but one number. And if I do p of n minus 1 XOR p of n, the value will be greater than n, which won't satisfy the index condition, as the indexes are always less than or equal to n. And if I keep n in between somewhere, here p of n XOR any number j. Here obviously if I have the value n at p of I, p of j will be less than n and this will be greater than n. And again this won't satisfy the index condition. What we want is p of I XOR p of j must be equal to I. As this value is greater than n, this equality will not be satisfied. So we can see that if n is a perfect power of 2, then our answer is -1. Okay. Now coming to the case where n is odd. What will happen here is that if the value of n is odd, we can see that the last bit will be 1. So what I'll do is I'll initially keep the value n at the end of the permutation. I'll make a construction. At the index n, n minus 1, n minus 2, so on. I'll keep the value n at the end of permutation. Okay. Now, if I XOR the value n with 1, if as n is odd, n XOR 1 will be equal to n minus 1. So, I can safely keep 1 here because at n minus 1 index, I have no other option other than to XOR with last element. So, 1 XOR n will be equal to n minus 1. So, I can keep 1 here. And after keeping 1 here, we can notice a fact that if the last element is 1, I can make a similar construction as I have done in C1. Like what we did in C1 is, yeah, if I is even, we have put P of I equal to I plus 1, and if I is odd, P of I equal to I minus 1. So after putting 1 in n minus 1 location, what we'll do is, if I is even, we'll put P of I equal to I plus 1, right? Yeah. If I is even, P of I equal to I plus 1, and if I is odd, P of I equal to I minus 1. And here we can see that this is odd, even, odd. So basically, at this index, we'll have the value, we'll have the previous value. Like for example, n minus 2, n minus 3. I'll have n minus 3 here, n minus 2 here. Similarly, n minus 4, n minus 5. I'll have n minus 5 here, n minus 4 here, as follows. And coming to the last two cases, what will happen in the last case is that 2, 3, 4, so on. 2 will have, as 2 is even, 2 will have the value 3, I plus 1, and 3 is odd, so 3 will have the value 2. Okay, 4 will have the value 5, and 5 will have the value 4. And the leftover value will be the value. Here I have put the value n, and here we are having the values n minus 3, n minus 2, n minus 5, n minus 4 at the indices. So the missing value is n minus 1. So the value here will be equal to n minus 1. As the value of n is odd, the value of, so n minus 1 will be even. So let the value of n be something, and as it is odd, the last bit will be 1. N minus 1 here will have the similar first, the initial bits will be similar to n, and the last bit will be 0. So if we take the value of XOR of both of this, we'll be left over with only the bit 1, and all the values, as the bits are same, it will be 0. So basically n XOR n minus 1 equal to 1 when n is odd. So I can safely put the value, remaining value n minus 1 here. I'll show the code for n, show the code for the case where n is odd. When n is odd, I'm putting the value of I'm putting the last element of the permutation as n and the previous element as 1. And all the remaining elements I am doing it similar to what I did at C1. Like if it is even, I'll put I plus 1, and if it is odd, I'll put I minus 1. And the remaining value will be n minus 1 here. So after putting the remaining value, I'm printing all the elements. So we have handled the case where n is equal to odd. And also here initially I'm taking the bit seal of the value n. And if n is equal to the bit seal of n, then it is a perfect power of 2. Then I'll simply print minus 1. So now coming to the case where n is even. So here what I'll do is I'll find the first set bit of the value n. I'll explain it. So we have handle the case, handle the -1 case, and handle the case where n is odd. Now coming to the case where n is even, as n is not a power of 2, it has at least two set bits. So what I'll do is, as n is even, the last bit will be 0. I'll find the first set bit of n. Like for example, let n be like this. This is the first set bit of n. Hmm. Or I guess it's better if I directly go with the construction. What I'll do in this case is, initially I'll put the last element as 1. And like I did before, if the value of permutation is even, sorry, if the value of index is even, if I is even, then P of I will be equal to I plus 1. Else, if I is odd, P of I will be equal to I minus 1. Last element will be 1 and the previous element will be odd element. So if this is n minus 1, n minus 2, here the value will be n minus 2 and n minus 1, so on. So initially I'll make this construction, but if I make this construction, I'll have a problem at index 1. So what my next idea is that I will, uh, I have initially found the first set bit right in the number n. So let the first set bit be at a position z. So at the index 2 par z, 2 par z will be basically 100 in the above case. This is 2 par z. So at index 2 par z, I am planning to keep the element n itself because if I keep this value, the value I have to XOR with the current 2 par z will be, like for example, z, let these be any random bits. So I have to XOR with a value, the bits here, and the initially set bit will be 0, so on. So if I XOR n with that value, what will happen is I will be getting a value 2 par z. I'll be the answer of solve will be 2 per z. As the first bits will be same, as the bits will be same till z, and only what I'll do is I'll insert the z bit. So in n, I'll just remove the 2 per z bit in the value n. Basically, this is similar to n XOR 2 per z. Let this number be y. It's obvious that the value y will be greater than 2 per z because this number has at least two z bits. Like as the number n has at least two set bits, it has a set bit 1 which is greater than z. So we can safely say that y is greater than 2 per z, as we have the pairs n minus 1, n minus 2, n minus 2, like here n minus 3, n minus 4 indices. Here we have n minus 4, n minus 3, so on. So we can say that this value y, which is greater than 2 per z, has been already covered in this sequence. So on, and let the index z be here somewhere. The value y will be already covered in this sequence. So what I'll do is, if I place n, I'll just pick the location where p of j will be equal to y, and n XOR p of j will be equal to 2 per z, which is nothing but this is 2 per z index, right? Which is nothing but our index I. So I can safely place n equal to 2 per z here. If I go on filling like this, like for example at even I plus 1 and at odd I minus 1, I am just altering the value currently at index 2 per z, right? So all other indices contain the values in this format. Even I plus 1 and odd, if it is even I plus 1, and if it is odd I minus 1. Okay. So currently what I did is at 2 per z I kept the value n. So the value that is supposed to be there at 2 per z will be 2 per z plus 1, as 2 per z is even, and the value of p at that location will be 2 per z plus 1. What I'll do here is uh, I have all the other values set and only 2 per z minus 1 remaining, right? So I will keep the value 2 per z minus 1 at the first index of the permutation. So here, in order to satisfy this, in order to satisfy an element j such that p of 1 dot XOR p of j will be equal to 1, the value of j must be equal to p of 1 is 2 per z plus 1, right? XOR p of j equal to 1. This will result to p of j equal to 2 per z. Okay. Uh, or to explain in more detailed way, 2 per z plus 1 XOR 1. 2 per z plus 1 will be something in this format, and after XORing it with 1, the last bit will be answered and we will be left with 2 per z. Okay. So p of j is 2 per z. As in the permutation, all other elements are covered. Like only we are unsure about the first index, and all other elements are covered. So, like they there will be an index which has the value 2 per z. Okay. So if we place 2 per z plus 1, we can safely pick an index j such that p of j equal to 2 per z. And if we pick that j, what we'll get is p of I or b of j, that's equal to 2 per z plus 1 or 2 per z, that's equal to 1. In this way, this is satisfied. Like what I have done here is basically I have filled this initially, and at the index 2 per z, at the index 2 per z, the current value I have is 2 per z plus 1. If I fill like this, what I'll do is uh, instead of 2 per z plus 1, I'll keep the value in here, and I will take the value 2 per z plus 1, which will be the only leftover value at index 1. And that is my construction. Coming to the code, what I'll do is initially I'll find the first set bit, and after getting the first set bit, what I'll do is I'll basically proceed with the initial construction where if I is even, I'll put I plus 1, and if I is odd, I'll put I minus 1. And what I'll do, my goal is to put the value of A of P. Here P is the first set bit, right? A of P as N and A of 1, the value at A of P. So what I'll do is I'll put A of 1 equal to N and swap the values at position A of 1 and A of P. A of 1 and A of AP. After swapping them, I'll simply output the permutation. And that's all. In the contest, actually, I have made a check function just for safety, like for checking the small n values if the permutation I am outputting is correct or not. Of n square check function, I guess. And that's all. Now, coming to the fourth question, we are given a string of size n consisting of characters 0 and 1. We define f of w as number of permutations from containing the number of permutations of array containing elements from 0 to n minus 1 such that for all I from 1 to n following holds. If w of I equal to 1, there must exist an LR such that mix of the range LR in the permutation will be equal to I. And if Wi is 0, there should not exist any range LR such that mix of the range in the permutation will be equal to I. Okay. In this version, the string doesn't contain any question marks. So what we have to find the smallest value among all such strings. Like as the string doesn't contain any question mark, there is only one string that is possible. We have to find the value of f of w of that string, and that value should not be divisible by c. And since the answer can be very large, we have to print it modulo 1e9 plus 7. Here, the values of n is bounded by 2e5 and c is bounded by 1e9. And string contains only characters 0 and 1. So coming to the code, here the value of n is from 3 to some multiple of 1e5. Okay. So let's first see the cases where our answer will be minus 1. Okay. Basically, what we have to find is f of w, that is number of possible permutations satisfying the conditions. Okay. So let's first analyze the case minus 1. Number of, and also this should not be divisible by c. So if the value of c equal to 1, 1 divides all the numbers, so our answer will be minus 1. In the second, also if w of 1 equal to 0, like basically what this means is there does not exist any LR such that mix from L to R in permutation equal to 1. So this is false because uh, let the permit as the permutation size n is greater than or equal to 3, for any permutation greater than or equal to 3, what I'll do is I'll take the value LR, like let 0 be at index 2. I'll take the value of LR to be 2 comma 2 and max of 0 will be equal to 1. So I can simply take the LR to be the index of 0 and max will be 1. So it's impossible to have W of 1 equal to 0. Also the case W of n equal to 0 is impossible because after placing all the elements from 1 to n minus 1 in the permutation, like because as we have all the elements from 1 to n minus 1 in the permutation, if we take L equal to 1 and R equal to n, that is basically the whole permutation, mix of the whole permutation will be equal to n. So W of n equal to 0 is also minus 1. And that's all. So we have handled the case minus 1 here initially. So coming to the other case, what we have here is W of 1 equal to 1. Now, suppose if we have W2 equal to 0, initially, let's suppose I have 0 and 1. Let me place the elements one by one in the permutation. Like initial, I'll place 0, 1, 2, 3. 0 is the first element that I have in the permutation, and I can place 1 anyway, either to the left of 0 or to the right of 0. Okay, I'll place 1 here. If if I want to have W of 2 equal to 0, I have to place 2. When will my answer will be 2? When I only uh, take a range L comma R in the permutation P such that it contains 0, 1 and doesn't contain 2. So in order to remove all such ranges LR which only contain 0, 1 and not contain 2, I'll place 2 somewhere in between 0 and 1. So if I put it like this, either I can get a max 0, max 1, and it is impossible to get max equal to 2. Because if I take a range L2R containing 0 and 1, it definitely contains 2, and my value of max will be greater than or equal to 3. Because max of 0, 1, 2 equal to 3. So, generalizing this, what my plan is that not a generalize. We have handled the case where W2 equal to 0. If W2 equal to 1, what I'll do is I'll put the value 2 in either of the ends of the array. Like I'll put the value to the left of 0 and 1, or I'll put the value to the right of 0 and 1. So when W2 equal to 1, I have two choices. Either end, either ends of the current permutation. So I'll generalize this. If W of x equal to 0, what I'll do is currently I have put the elements till x. So uh, if W of x is equal to 0, I am allowed to put the value of x. Like for example, I have all the elements 1, 2, 3, so on till put till x minus 1 actually, as we are trying to make the max of x as 0, right? 3 to x minus 1. So I am free to put the value x in any of the gaps. So what I'll do is I'll put text in between existing numbers. Or basically I'll put text in the gaps, in current gaps. Like for example, if I have to put x, I have 0 to x minus 1, that is x elements. As I have x elements, there will be x minus 1 gaps. So if w of x equal to 0, I have x minus 1 ways to put x. And if w of x equal to 1, so if the value of w of x equal to 1, I have initially 0 to x minus 1. Like they are not necessary in ascending order, like they can be in any random order. So as the w of x equal to 1, I can put the value of x in either of the ends, either here or here, either to the left side or to the right side. Because if I put it at either of the ends, I can get the value if I take this subarray or if I select this range L comma sorry, I want the value of I want to have any range LR such that the mix equal to x, right? So if I don't keep the value x in between these current existing numbers, then I'll take the current range LR endpoints as follows, and the mix of this will be equal to x. So simply, if I place x outside this range, then I can have a range such that w of x equal to 1. So what I'll do is I have two options, either to the left or right. So two ways to put x, either left or right. So what we can see here is if w of x equal to 0, I have x minus 1 ways. And if w of x equal to 1, I have two ways. And that's all. What I'll do is I'll iterate over all indices from I equal to 1 is already set, right? W of 1 equal to 1. So I'll iterate from uh, I equal to 2 to n. And what I'll do is initially let my final answer be uh, like I'll keep a count of all the number of possible ways in a variable answer. Initially, we have 0, 1 in the array, right? Because I'm iterating from 2. 0, 1 can be can have two configurations, either 0, 1 or 1, 0. So I'll initialize my answer with 2. And for all I equal to 2 to n, if w of x equal to 1, then what I'll do is answer equal to answer into 2. Else answer equal to answer into x minus 1. Here also there is another catch. We have to see if the value of answer is divisible by C. So what I'll do is I'll maintain two value of answer is divisible by C, and finally we have to output answer mod 189 plus 7. Let this be mod. So I'll maintain two versions of answer because if to check whether it's divisible by C, I can't just multiply all the values and finally apply answer modulo C equal to 0 because in this multiplication it will overflow. So after every multiplication, I'll maintain another copy of answer in Cans, uh, or I'll simply make a copy of answer. And after every multiplication, I'll do one of the answer modulo equal to mod, or one second, modulo equal to 1 in n plus 7. And I'll make the copy of answer modulo equal to C. Okay. So finally, what I'll check is if my copy of answer equal to 0, then my final answer is a multiple of C. So I'll print -1. Else, I'll print the value of answer. Answer as after every multiplication, I'm taking the modulo. This will be modulo 1 in n plus 7. That's all. Now coming to the code. Here initially I'm taking the string W at input as input. And my goal, and I have made a vector of characters. The main reason is that I want the string to be one index. Like for example, if s of 1 is 0, I want to know that the mix cannot be 1. So after making the string one indexed, initially I am checking the -1 case. If s of 1 is 0 or s of n is 0. If it is given that the mix can't be 1 or the mix can't be n. And the third condition is that the value of c can't be 1. If either of these three conditions is there, then I'll return with -1. So, as discussed, I'll initialize the current value with 2. That is the case where 0, 1 and 1, 0. And here I am maintaining a copy of answer. So, in the case where the value of uh, W or S in this case, in the value of S is 1, what I'll do is I'll multiply current with 2. That is either of the ends. I can place the value I at either of the ends. So I'll multiply it with 2. Else, what I'll do is I can place it anywhere in between, right? So number of gaps is I minus 1. So I'll multiply current with number of gaps and also copy of answer. And here we can see that taking modulo with 199 plus 7 in current, and in the copy of answer I am taking modulo with C. Now if it is divisible by C, if my final answer is divisible by C, I'll output -1. Else I'll print the value current. And that's all.